discrete digital, or I should say in the discrete domain. But there's a simple transform. It may be termed different things. It's a bilinear transform where you can actually take a function in h of s and by a little sleight of hand, find the translation between s and z and then create a function in z. Now remember, z is discrete time, that will implement that same filter action in the frequency domain. You understand me, class? I'm going to show you that's a very powerful tool, and you'll remember this later on. The second thing I'm going to do if I have time, and now the bilateral will be on the final exam, but I'll give you the actual transformation. I'm not going to ask you to memorize it. The other thing I'm going to tell you is I would like to go through an actual, the application of this to a real radar signal, not a fictitious one, but a real signal, and show you first what it looks like in the spectral domain and why windowing, without going overboard into the details of it, is so very important for things like Doppler frequency shift. Y'all know that that's the way all these moving target indicators work. Your K-band and X-band radars that the police use are all moving target indicators. They have nothing about the range to the target. It only gives you the velocity of the target relative to the actual person controlling the radar unit. One thing I failed to mention, and I need to do this here. Now, a Doppler shift is always measures the shift in frequency due to the velocity of a projectile coming at the radar from monostatic radars. It means if the radar is here, if a target's moving this way, then there's an apparent Doppler shift and it's measurable. And if it's coming at the actual radar, then the shift will be up in apparent frequency. And that, just always think of race cars and what you hear if you've ever been in a speedway. They come at you, it gets higher and higher pitch, right? They go by you, lower and lower. Anything moving away is a lower frequency than the apparent center frequency of the actual radar. Just remember that, that's important. But if something is coming, say a police cars, I use police because they're all around and they use radar. If I have a police here and he's shooting that direction, but a car's moving in this direction and he shoots it right at the point where it's a right angle, there's no differential velocity change. Follow me? He will measure a velocity of 0 with respect to you. If he's at 45 degrees and you're coming, then what he does is get the component of that velocity in the direction of his actual radar unit. And if it's 45, it's really 1 over the square root of 2, about 70% your actual velocity. Keep this in mind too. What police always try to do, and they know this, they try to get, and it's the same thing with everybody else that use radar for speed detection, to get a straight shot at you for the maximum velocity. They would like to be right in your path without crashing. Follow me, class? So just keep that in mind. I didn't mention that last time. It's very important. Now I'm going to mention the second thing. I don't want to spend too much time gabbing, but you have to understand something about this. Everybody knows, I think by now, that drones, unmanned aerial vehicles, as well as self-driving cars, everything is becoming autonomous. And there's a lot of artificial intelligence that is being used to direct and steer. Sensors are very, very important on all these things. They have both GPS to control the actual location with the global positioning satellites, with the network of, they use GPS, but they actually tab into the cell phone tower areas that they use that for. But radar on those things is essential, and here's why. It doesn't matter how well the terrain map is. All it takes is one bad storm and a few trees to fall down, and it's changed instantly. What they need is something on these drones that they're flying. Do you all know about how important that is? Do you know about Amazon and Google? They're putting millions of dollars. The governments of the world are. Our government is. They're doing it for military applications. But the post office is involved in this. They know that they can get rid of the mailman by getting things that fly the mail, literally, from a central location to you, if it's not too heavy, and just drop it. Instead of a mailbox, it might be a platform. They just drop it on and your platform grabs it, something like that, where they could activate it. Well, this is being looked at by everybody, and there's a fortune in it. And I don't know who's going to get there first, probably Google, but I'm just betting that way because of the money involved. They have a lot of money to burn. They need very lightweight radars. extremely lightweight. Things that can both send out a signal that can communicate information as well as interrogate a region of space for what's there. Now I'm telling you this because I'm telling you what's on the forefront. Well, understanding signal processing, windowing, stuff like this, gives you a leg up on a lot of people heading towards working in that market. Now, you're electrical and computer engineers, you're the first people they're going to try to get. They don't need just computer engineers, trust me, or computer scientists. They need people that understand the fundamental physics and how to apply a lot of the ideas. Because there's a lot of areas of problems. And I can tell you right now, have you heard about some of the accidents that have happened with autonomous vehicles? The Tesla car, and I mean, there's that one situation that's unforeseen that happens. Well, the one thing that'll prevent a lot of that is active sensors on board that can immediately brake and do things like this. But one of the cars, I'm not sure if it's Tesla, but they actually they have a visual ID thing that just looks at the lines on the road, and that's how it steers. Well, what happens if all of a sudden it's a blinding snowstorm, a dust storm, and the lines are gone? Now it's blind, and the guy might be asleep and the car crashes, theoretically. Well, those are the kind of problems that active sensors prevent because, especially radars, they can immediately find out if there's a problem and brake. I think Cadillac has the OnStar, and they had something like this. There was a problem around turns with if they had those, any kind of, well, what do they call these things? They're not the formal, there's a term for this, but you know the standard guardrails? When you have on a highway, they have a raised guardrail and stuff, and it's very sturdy. Well, when it goes around a turn, when a car goes around a turn, all of a sudden it looks like there's a closure velocity, or that you're moving into a harm's way, and so it would brake. So that was a problem, and they're trying to work around it. With active radars, you can get around a lot of that stuff. I mean, that was just I forgot the name of that sensor that they use. So that's why I'm telling you it's important. I'm going to get through these proofs or to show you some of these things that apply. And if you have questions, please ask me. I brought 3 books today. I've got a lot of stuff I'd like to show you. But I'm really going to show you first the binary transform before I do anything else. And what happened to my... Oh, there it is. Here, I'll get it. No, I got it. Thank you. Thank you very much. This is my go-to. Now, this is a question I'm ready. Why did you people choose electrical and computer engineering out instead of mechanical? Mechanical engineering has 3 times the students we do. I don't know why. I've asked other people, why did you choose EE and not mechanical, or not civil, or not chemical, really?
Computers.
Yeah.
I mean, I'll tell you what I did. But first, I'm curious about how. I might as well tell you. I love physics and stuff, and I absolutely love physics. Then I saw the salaries physicists made. I said, I don't love it that much. You're recording it too. All right, you can blackmail me later. But anyway, it boiled down to this. I love that, and I enjoyed electromagnetics. I enjoyed everything that had to do with wave propagation, and I love messing around with amplifiers, TVs, stuff like this. The stereo systems, before I knew even what I was doing. In high school, I took electronics. So it was sort of a natural thing. I enjoyed science and mathematics all my life. I didn't care for long memorizations of, I had to take these courses in geography and stuff when I was in high school. And where you had to memorize the gross national product of Argentina in the 50s, 60s, 70s, 80s, and compare it to gross national product of something like New Zealand. And it used to just bore me to death. I could care less. But science and math I love. And I especially love things that were, that showed there was a lot of cleverness in things, like Albert Einstein stuff I enjoyed reading about, didn't understand it. That's why I gravitated. Why did you choose it? Go ahead.
I started in the electrical industry. Like I'm an industrial control journeyman, and I've seen some of the old stuff they were doing with relays and stuff like that. Mm-hmm. And I've seen how they've condensed all that down into pretty autonomous stuff, and they're slowly phasing out people. And so
You got a natural interest in how they did it.
how they did it, and I want to catch that wave, and being able to create that and get
What
the
about you?
tangible.
You're a physicist.
Yeah, I'm gonna go to grad school for physics after this. So, yeah, I'll have you know I'm prepared to make no money.
I'll enjoy poverty. What about you? You're from Italy. Why did you choose?
Similar reason. In high school, they took me to see they have a physical research facility. They have an particle accelerator. I got fascinated by it, but didn't want to have the salary.
Are there any hackers in here, by any chance? I know one guy, I'm not gonna rat him out, who is, not with Anonymous, but he's with that, what's that group on Reddit? Not Anonymous, but, oh, I can't think of it. Anyway, they're all over the world. There are a bunch of guys that go out and they do things like take down websites of Scientology or something. I can't think of the name of it, but they do it, and he's very clever. That's the reason he got into it, because it was a natural thing. Hacking and things like that are all electrical engineering, programming type of stuff with Python, these languages. So but he also enjoyed the wireless side of it, figuring out how to get into routers and all that stuff. And he showed me a few things, and I don't trust him. I won't even let him near my office. But, and that made sense, but there are no hackers here, at least nobody will admit it. Anybody else? I'm curious. What about you? Yeah.
Well, when I was young, I built a CPU with my dad, and
A GPU?
a CPU.
Oh, a computer.
And that started like everything else.
You built a computer? A digital computer?
No, just a regular CPU.
Analog computer?
It was just regular CPU kit box. Like,
Was it a kit thing you built?
Yeah.
Okay. I remember I built a multimeter, a Heathkit multimeter one time. When I was, when you're young, you get these things. I don't know if do you remember these things, anybody? Heathkit? Nothing? No?
mm,
Well, anyway, it was a long time ago. I'm curious about you too. Your dad?
I mean, for me, it was kind of similar reasons to you. I've always been fascinated with like the physics and sort of getting down to the nitty-gritty of why things work.
Here's what I'm really trying to figure out, and nobody has answered this right, and I'm asking this because I have to talk to somebody, maybe not later today, but on Monday about this, and a pretty important person. Why not mechanical? Why not civil? Why not chemical? Mechanical engineers is sort of a natural for guys that play with cars. If you want a really powerful car and you spend some time modifying it, mechanical seems like a logical way to go if you got the brains.
There's
Just
really,
does.
There's not really anywhere to go in mechanical. Like all the forefront of technology now is all electrical. Like everywhere we're going is electrical.
I messed with cars, but I didn't go mechanical.
Well, I mean, I'm going to tell you this much. It's a question I have, and nobody has been able to answer this question because the number of people in mechanical engineers around the country is about 3 or 4 times that of any other field, any other engineering. And it's, mechanical just doesn't mean mechanical. There's hybridizations where you get mechanical, electrical, like if you know David Beverly, he does a whole bunch of stuff with GPS and all sorts of stuff. It's never just one engineering. I was told that when I was where you're sitting as a sophomore, actually. We were told that all engineers blend, they overlap, and I use more chemistry than I ever thought I would as an electrical engineer, electrical computer engineer. You're more or less tabbed to do anything you can do in the real world, and so you use a lot. However, a person in chemical engineering knows a heck of a lot more about developing stable reactions for chemical reactions than you or I do. It's just not in our wheelhouse, but we might at least have an appreciation for what they're doing, where people in, I don't know, our history just clueless. At least you guys. All right, I'm asking you that. If you want to talk to me about that afterwards, please do. But that fascinates. Now I'm going to go through. I get to ask this because we're in our last week or so, and I always do this. Now, what I want to show you is how to take a function, a filter that you actually understand, an analog filter in continuous time, and build a digital filter that will, or I should say, a discrete time filter that will do the same thing. Now follow me on this. So first I've got to go through the basic filters with you. This is in the chapters, the earlier chapters. I'm going to just tell you this. If you talk about a low pass filter here, and then we'll talk about high pass, but for a typical low pass filter, there's a couple of ways to do it. Just for a simple first order filter, nothing very complicated. Probably you can do it this way. I mean, there's several ways. If you just want to say that I have a capacitor C and a resistor R, and then I have my input here. This is going to be my, I'll call it X of t here. My output here would be Y of t. And if you look at this, you could do it in the continuous time domain, but it doesn't help. It will not help you. It's best to do it in the actual, find the transfer function for this system in the frequency domain. And the S domain, frankly, is the best way to do this. So if you take a look at this, this is the input, this is the output. If you do this in the S domain, the impedance of this is 1 over CS, right? And then you can find the output versus input relationships, or you can say that H of S for the low-pass system being equal to Y of S over X of S. And remember, Y of t will become Y of S, and X of t will become X of S here. So this is the output, this is the transfer function. Well, here, Y of S, this is simple voltage division, so it's that impedance. So it would be 1 over CS over 1 over CS plus R. Do you all agree with that, class? Simple low-pass filter, agree? Now, I'm going to go ahead and make it a little more compact and understandable. I'll multiply top and bottom by, say, by 1 over CS, so I get 1 plus RCS. And then I'm going to divide top and bottom by 1 over RC, so I have 1 over RC over 1 over RC plus S. And why did I do that, anybody? You know me pretty well. What's the goal here when I'm doing this? Coefficient of S is 1. That's what I'm after. All right, class? That's the one thing I want. So this is a simple low-pass filter. And if I took a look at this, and I'll do the property here, if I let S become J omega, so now we're going to look at the property of this filter in the frequency domain, then the actual magnitude of, now it would be H of omega here, would be equal to 1 over RC over the square root of 1 over RC squared plus omega squared. Remember, S becomes J omega, right? And so I have 1 over RC plus J omega. The magnitude of that is going to be this term squared plus the magnitude of this term squared. You don't square the J, in other words. It's just a plus omega squared. Do y'all agree with that? Now, if you take a look at this, and I'll put it here. Actually, let me do it here. This filter, I'm just going to do the whole thing. If I plot it versus omega, and this is the magnitude of H of omega, almost always, the way they do these, almost always, on this axis, for filter behavior, they're going to plot 20 times the log of the magnitude of H of omega. That's almost always the way it goes. That way, this will be in decimals, you might say. Follow me? It's usually a ratio of H of omega over something, but just H of omega is fine. On this axis, it's usually a logarithmic axis, so it would be like and this might be 10, this 100, this 1,000, and this 10,000, and so forth in frequency. Are you with me? Now, when they take a look at this and plot this, for small values of omega, matter of fact, we're just going to say this. If I say that 1 over RC is equal to 10 or equal to 1,000, well, as long as you're much less than a frequency much less than 1,000, when omega is much less than 1,000, then this term dominates, and the ratio of these two is 1. Do you agree with that, class? If you just forget about omega because it's so small, I have 1 over RC divided by the square root of 1 over RC squared, which is 1 over RC, and I have 1. Well, 20 times the log of 1 is 0. Is it not, class? So it's just going to be, you're going to find a point up here, 0, and it'll stay that way until I hit 1,000. And now, when omega is 1,000, all of a sudden, this is comparable to this. It's identical to this at 1,000, right? Just listen to me on this one. Now, if I have these two numbers that are the same, that's really 2 times either one of these numbers, isn't it? Say it's 2 times 1 over RC squared. Well, the square root of 2 can be factored out. So I have 1 over RC divided by 2, square root of 2, pardon me, times the square root of 1 over RC squared, or just 1 over RC. I have 1 over RC over the square root of 2, 1 over RC squared. Or at this point right here, now the 20 times the log of that business really is 20 times the log of 1 over the square root of 2, and that is about minus 3 dB. If you go ahead and do that, just do this for me. Take the log of 1 over the square root of 2 times 20, or just the log of square root of 2 times 20. It's really 10 times the log of 2, it's the same thing, minus 10 times the log of 2. It's about minus 3 dB, I think. Y'all see that? Is it 3 dB? Was it 3.1 something? All right, it's minus 3.3 dB. Now this is an important frequency because that's called literally the 3 dB frequency. It's the first break frequency. And then after that, this thing's going to keep going down at a rate of minus 20 dB per decade. So from here, from 1,000 to 10,000, it'll drop by 20 dB. And the reason is this is a 20 out in front of this right here. And there's this, I'm not going to go through the whole thing, but it will. This is basic filter properties. All right, you can build a filter, a low-pass filter, and you can choose 1 over RC to be 1,000, and that means this is going to be the actual frequency cutoff, right? Now suppose we're going to apply this exact filter. We want the same behavior to a sampled signal. Follow me? This is the bilinear transform. So I'm going to try to show you that. I want to put the filter up first so you get an appreciation. And you all agree that we could make that low pass cut anything we want. We could just 1 over RC dictates where that frequency is, correct? You choose R and C, you can make it as low as you want or as high as you want. But the general shape will always be the same. We just shift where that cut frequency is. Agreed? All right, now, how would you do this with real digital filters or discrete time filters? So now, we first look at 2 things. I'm going to go ahead and put up what x of s is. We know it's the integral from 0 to infinity of x of t e to the minus st dt. Do you all agree with that? That's just a basic definition. And when I go ahead and I put x of z down, x of z, I know that's a summation, right? From n equals 0 to infinity of x of n times z to the minus n, right? Now, part of this we did before. This is important you see this. Now we take a look at this stuff for 1 second. We know this is a sampled signal. I can go ahead and make this a sampled signal and say that this is really going to be the integral from 0 to infinity of x of t times the summation n equals 0 to infinity of delta of t minus nt, ts, that's a sampling frequency, and it's times e to the minus st dt. Then I can go ahead and say that in fact, actually, here it would be better to do convolution, but I'm not going to. I'm just going to leave it like that because this is the way your book does it. If I take this and I go ahead and say that because this only is on at NTS, I can replace this argument by NTS. And then I can take the operation, since that is at a given point N and TS, not a function of small t, I can take the integration inside, and then in doing that, I have the summation outside, and I have x of NTS here. And then I have integral of that, and it's going to come out to be the summation It'll be e to the minus n ts. I'm sorry, n e to the minus quantity nts times s. That should be ts here. Maybe I'll just leave it as t. And I'm going to tell you here, at this point, without spending a lot of time on it, I want you to just understand something. There's something else that I'm not saying about this, that I'm trying to just focus on the bilinear transform. If you look at this just for a second, you'll notice this and this are identical. Remember, with the n in there, we suppress the ts, so we get rid of that. So this would have to equal to this. That means I have z to the minus n is equal to e to the minus n ts times s. Are you with me? Try to appreciate what I'm doing. I want to find a conversion so I can take a filter in the S domain and just find a transform for z, replace s by some, transform of z so I can get this filter and literally have the h of that filter in the z domain. That's my goal. All right, just work with me on this one. Here, y'all agree that if that's the truth, then that exponent, e to the minus nts times s, has to be equal to z to the minus n. The n can go away. Do you agree with that, class? Yeah.
Where did the extra is
This is t sub s, just means the sampling
Oh, so
interval.
it's-
S is the actual,
come? I thought it was time.
no. So I come down here and I can get rid of the n. So I have z, really, actually, I can get rid of the minus signs too if I want. So now I have that. I have z is e to the st, s times ts. Ts is it's that sampling interval. So now if I take natural log of z here, that will be equal to s times ts here, or I can take natural log of z divided by ts is equal to s. I'll write that down right there for a second. And also, because of that, you can also get z, and I'll put this over here, z would be equal to, I don't want to throw out the proof on this one, is equal to 1 plus t, this is really ts over 2, times, that's good. I need to do this first. I gotta tell you one thing, this, you can get an approximation for the natural log of z, and that's gonna be z minus 1 over z plus 1. So I can say that this furthermore can be approximated as 1 over ts times z minus 1 over z plus 1. This is an approximation now for the log of z. Has anybody ever seen that before? Have you ever seen approximations for logarithms at low values? It is an approximation that is legitimate. So this is the one we're actually going to use, not that, because that would be too complicated. We're going to use this approximation. You can actually try it if you don't believe it. You can take like a log of 2 and just take 2 minus 1 over 2 plus 1, and you're going to find it's very close. So now, if I have that, this is, remember, this is for s. Then I can say z, based on the second part, can be rendered as simply 1 plus ts over 2 times s over 1 minus TS over 2 times S. And again, this is a simple relationship between Z and S. And now I go a step further. I wrote this stuff down because I want to make sure that what I'm doing is I don't put anything on the board that is precisely correct. Now remember, we were using Laplace symbols, really. We're using S, not omega. But now if you take this transform here, and now we just let S be equal to j omega, that would be at a constant frequency. Now I'm going to have j omega here on this side would be equal to, and I'm going to go to this one, 1 over TS here times, and instead of Z, I want to be in the just in the frequency domain, I'm going to replace Z by e to the j omega. Let me explain what I'm doing here. You all know the S domain encompasses the j omega domain, encompasses the Fourier domain for functions that have values that are only non-zero for t greater than 0, right? So we can take a Laplace transform and just replace S by j omega. Now we're into the Fourier complete frequency domain, right? We have nothing to worry about. We can also take Z, and if we let rho equal 1, now we're in the discrete time frequency domain. Now we have gotten rid of that, you might say, really damping effect of the value of rho in front of e to the j omega, right? When it's 1. Now when you do this, now we're relating continuous time frequency to discrete time frequency, capital omega. This is very important, right? So then if we do that, then this becomes e to the j omega. This one I'll do minus 1 over e to the j omega plus 1. At this point, I've got to ask the class, let me get rid of that. What do you think I'm going to do next? Because remember, we have the transform in S, right? We can simply take that transform I had here, that simple one, and I can replace S by Z, right? I can go ahead and say S is equal to this, and I can plug it in there, but that would be a little too awkward. What I'm going to do is replace S by j omega in there first, and then find out what omega is in terms of capital omega. Are you with me, class? Just work with me on this one. Now, watch what happens here. What do you think I'm going to do with this? I know some of you are going to see. What would I like to turn that into to make it a little more operationally easy? Yeah, I'm probably going to try a sine trick in there, sines and cosines. So for the top one, I can say, let me go up here. I can say that this j omega here would be equal to, well, it's 1 over TS here. This looks like what? E to the j omega over 2 times e to the j omega over 2 minus e to the minus j omega over 2. And the bottom one looks like e to the j omega over 2 times e to the j omega over 2 plus e to the minus j omega over 2. Y'all agree with me so far? Remember I did the old trick of factoring out the e to the j omega over 2, correct, class? Now I'm down to this point. And I'll put over here the relationship. So I know that sine of really omega over 2 is equal to e to the j omega over 2 minus e to the minus j omega over 2 over 2j. And I know cosine of omega over 2 is equal to e to the j omega over 2 plus e to the j omega over 2 over 2. You all agree with me there? Okay? We've done this a lot of times. I'm going to multiply this by 2j, multiply this by 2. And now I simply substitute. Come down here and I have j omega is equal to 1 over TS times e to the j omega over 2 over e to the j omega over 2. That cancels and becomes 1. See if I can get a little bit better here. All right. And then the top one here is going to be 2j times the sine of omega over 2. The bottom one becomes 2 times cosine of omega over 2. Please just take a look at this. Do y'all agree with me first? In the back there, can you guys see this? You're waiting for the bottom line, but please follow me on this. Now, this cancels entirely. That's just 1. I've got a 1 over TS, and then here, you all see the 2's cancel? Class? What else cancels, please? Follow me. The J's, yes, that's the key. So now I have a transform where I can say 1 over TS times that. Can I bring it down even further? Class, think.
Yes.
What?
Tangent.
Tangent, right. It's 1 over TS times the tangent of omega over 2 is equal to omega.
Shouldn't
Now.
it be negative tangent though? It's negative sign.
No, it's positive, isn't it?
And maybe your line's just got a little space in it and it looked like
I'm
it.
sorry, no, they're not, it's not, sorry about that. No, it's just sine over cosine. It's tangent, isn't it? Now listen to me. That means omega can be replaced by 1 over TS times tangent of omega over 2 in the continuous time frequency, the actual, the h of s, take s, turn it into j omega, and then replace it by this, and you've got, in fact, something that you can use for digital filtering. And that's just a tangent function. I'm going to do an example too if I have time. And by the same token, I didn't put this up here. This is the opposite relationship. If I put TS times omega, and then I take this, I take tan minus 1 of it, and multiply it by 2, now I get the omega that would be related. So, all that said, here's how this works. Now, if we have our function, our h of s, was actually equal to 1 over rc over 1 over rc plus s, correct? Right. If we want to go right into the s, we want to take this, and we want to go right into the z domain. We want an h of z. You'll notice that s was equal to what? 1 over ts, right, times z minus 1 over z plus 1, right? That was the relationship. If we want to just go in the z domain, right, this would be for the z domain. Just listen to me, all right? So if we want to do that, we could go ahead and say that this would be 1 over rc divided by 1 over rc times that, plus 1 over t. I'm just going to leave it as t instead of ts. And then it would be down here, z minus 1 divided by z plus 1. Now, you can see if I multiply top and bottom by z plus 1, I get 1 over rc. Matter of fact, what I'm going to do is take 1 over rc here and just call it equal to 1 over tau. So then I can get this as 1 over tau, and then it's going to be times z plus 1 over 1 over tau times z plus 1 times, or plus 1 over cap t times z minus 1. Are you with me? I'm just going ahead and I'm trying to expand these things. Are you with me, class? You see what's going to happen next? On top, I have 1 over tau, right? Then I have z plus a 1 over tau out there. Over here, well, I'll tell you, let me get, before I break it down like this, I'm going to do this. I'm going to multiply top and bottom by tau. to get rid of that and just have now a tau up here. Follow me on this? I'm trying to condense it, make it easy to understand. With me in the back there? Now that I get this point, I get the coefficients, and I group the coefficients of z and the constant. So I have z plus 1 here. And then, if I look at this for the coefficient, I have 1, and it's minus tau over t. And then I have plus, and then it's going to be 1 plus tau over t times z. Are you with me? Class? Now, when I look at this right here, this actually can break down to two functions. I can get this equal to z over 1 minus tau over t plus 1 plus tau over t times z plus 1 over 1 minus tau over t plus 1 plus tau over t times z. And this is now my h of z that I could implement. And I'll tell you in there. Okay? Now, if you look here, remember the whole thing about this is that the relationship between z itself right there, this is like we're building a filter. Now, we're using this just like we had S to build a filter. When we get the frequency response, we'll replace Z by e to the j omega, or j capital omega, right? But right now, you all remember Z is equal to e to the j omega if rho is 1, and that's if we want the frequency response or something. But this is right now the filter that we can build. Now, do you remember that if we're going to build these filters, do you remember how discrete time signals or discrete time equations, difference equations, turned into Z transforms? Do you all remember this? Just briefly. Let me just do this here, because before I do this, I want to make sure we're all on the same page in this. If I had like y of n plus a y of n minus 1 was equal to x of n, right? Now that's a difference equation, correct, class? How did I get it? I mean, I created it. What is the z transform of this? First, what is the h of z of this? Well, this would be what? Y of z plus z to the minus 1 times y of z, correct? Is equal to x of z. This is assuming what? No initial conditions to worry about, correct, class? No initial states. So I could therefore go ahead and say that y of z here over x of z was simply equal to 1 over 1 plus z minus 1, or z over z plus 1. Either one is correct, right? You remember doing this? Now, if we have this right here as our h of z, I know that's equal to y of z over x of z, correct, class? Just let me finish this thought. Now you'll notice I can go ahead and multiply x of z by this. Multiply y of z by that, and x of z over here. And I would get, you let me finish this? I'll be nice to you this week. I'm going to take x of z times z plus 1 equal to y of z follow me, y of z times 1 minus tau over t plus 1 plus tau over t times z, correct? Now, we're going to turn it into a difference equation, all right? Here's what you can do. Because z, we can divide both sides by z. With me? Just work with me on this one, and I'll leave you guys go. If we divide both sides by z, that becomes 1. This becomes z to the minus 1. This becomes 1. this becomes z to the minus 1. Are you with me? Now we're going to create the difference equation. Let me do this last step and I'll let you go. Are you with me with what I'm up to? All right, let's create the difference equation. What do I get? X of, come on, n, right? There's no z to the, right? X of n, right? Plus, what? X of n minus 1, correct? Because it's, please follow. This is not hard, but you gotta force, is equal to what? It's gonna be what? Coefficient is what? 1 minus tau over cap t. You gotta put that coefficient first, right? And then it's y of z minus 1, so it's gonna be y of, say it? Then you gotta put this coefficient plus 1 plus tau over t times y of n. And now you have a filter. Listen to me. If the sampling on this is tau s, that sampling frequency is used, and tau is 1 over RC. Tau is RC, pardon me, not 1 over C. Tau is RC. Then if you take a digital signal and you sample it at that rate, T of S, and you apply this difference operator, by the way, this is done in what, a discrete time domain. You take a value of a sample, you've got to store that value of a sample minus 1, you add the two together, right? That's equal to this, and what happens? This y of n minus 1 goes on that side with that coefficient, and you get the y of n from the previous value of y, and of course you have to divide that by 1 plus tau over 2, but you all see how now you've got a continuous time filter that you're very familiar with. You want that when you're sampling the signal, you want that signal to undergo the same filter properties, low frequency filtering. So now you can just take the filter that you're familiar with, do the transforms, and I did it only in the z domain, and now I have a difference equation that's easy to do. All right, sample and hold, store, and now you've got a discrete time filter that does the exact same thing as a continuous time filter. And this is important. This is the beginning of sort of a lot of the stuff that we're going to see. All right, next week I'm going to go through more in-depth problems about this. And I may give you, if you do me one favor, if I give you 2 problems, just do them for me so on Monday I can talk about it. I'll be happy. All right? Thank you. Did this make sense to y'all?